value C1 here, C2 here, like this. Probability that X takes the value Ci is the measure of this. Okay? So when you do the experiment, one of these occurs, something in omega occurs. Okay? It might be in A1, it might be in A2, whatever. Like the throwing of a die. See, I may divide the throwing of a die into even and odd. The outcome is either even or odd. So I can talk about what is the probability that it's even. Okay? What is the probability that is odd? In the regular case, it will be 1/3 or half. The same thing here. So probability of each of these events is defined. So that determines the probability for this random variable X. Okay? Same thing we do here. So if I have this way, X equal to summation Cj Pj, Cj belong to R, and these are mutually orthogonal and they add up to identity. This is nothing but then the spectral decomposition for X, right? If I assume that the Cj's are distinct, this is just the spectral decomposition for X, right? So using the spectral decomposition, I can say that the probability under rho that X equal to Ci. Okay. Let us assume that C1, P2, Cn are distinct. Because otherwise some probabilities would merge together. Is trace rho P.
Assume that without loss of generality, because otherwise you just merge the subspaces.
Yeah, basically. So without loss of generality. Okay. So probability that X equal to Cj is trace rho P. So in other words, if I have the spectral decomposition for X, then I can compute the probabilities. Okay? So a general random variable then would be something like this. In other words, say it's a linear combination of projections. So it will be with the real linear combination of projections. So any general random variable would be just a self-adjoint operator. Okay? So again, we start with bounded self-adjoint operators. So later on, actually, one can even consider unbounded self-adjoint operators. But for now, we take only bounded self-adjoint operators. So a random variable is replaced by what is called observable. So that just means X is a bounded operator of an H, which is self-adjoint. Okay. And if I have a spectral decomposition of X like this, then I can interpret it saying that X takes the value Cj with probability trace rho Pj. Okay. And more generally, if I may have a spectral measure, and the same kind of thing you can do. Okay. If you write X is as an integral,
so you need self-adjointness so that you get the Ci's to be real.
Yes, exactly.
So
yeah.
vice versa.
Yeah. Because we talk about real value random variables, so that's why it is. And once it's self-adjoint, you have the spectral theorem. You get a spectral decomposition of X like this integral at EDX. I can have a spectral measure on the real line, right? So which is sends Borel subsets of R to projections on H, right? The spectral measure of X. The last time we did this X. So with that I can talk about probability that X belongs to a subset of real line. Okay, under O. Okay, if I take a Borel subset of real line, I want to talk about probability that X belongs to B. So that is trace rho times the spectral projection. Okay, at B. Trace rho E, which is a genuine probability distribution actually. Okay, in the classical sense, it gives you a distribution on the real line. Okay. Let us see that might look very abstract. So 5 minutes let me explain one example. Nice example. take H as just C. And T of H, of course, the projections on H. And then rho is this operator. It's a positive operator of case 1. It is basically the projection onto the space spanned by E1, the basis vector E1. And I consider two random variables, okay, or observables. Okay, so here is the first one, x. We take half, 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 half. Y is same as rho. Okay, so now this x is a self-adjoint matrix. So I am thinking of it as a random variable, right, as an observer. So I can say what are the values taken by x and what are the probabilities. Okay. So for that I need to know the spectral decomposition of x. But the spectral decomposition of this is easy, right? This is just a projection, right? So this is the spectral decomposition of x is just 1 times this. So this is a projection. Plus 0 times I minus this. That is the orthogonal projection, which is okay. This is a spectral decomposition of x. Okay. So if I now compute, so what are the values taken by x? So the values taken by x are the CJs. In other words, the eigenvalues of x, right? So x takes values in 0 or 1, because the eigenvalues are just 0 and 1. Okay, the spectrum of x is a projection, so just 0 and 1. Okay, and I can talk about what is the probability that x equal to 1. For x equal to 1, corresponding to 1, the spectral projection is P. Right? Or this one, half, half, half. Right? So this is trace rho times this. Which is trace of 1, 0, 0, 0 times half, 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 half. Multiply out and take the trace, and you get it as right? And probability of rho x equal to 0, so these are the only two possible values. So this trace rho times the other projection, and you get it again as half. So this is like a Bernoulli. X is 0 or 1 with probability half each. Okay, so it models the Bernoulli. Okay, equally likely x takes the value 0 with probability half, x takes the value 1 with probability half. Okay. What about the other random variable? Again, I have taken a simple situation, just a projection. It's also a projection. So y takes values in, so the spectral decomposition of y is 1 times this projection, plus 0 times I minus this, which is this projection. And under rho, probability that y equal to 1 is the trace rho times this. Rho is same as this, and take the trace, you get 1. And probability that y equal to 0 is the trace rho times this one, and the product is 0, the trace is 0. So this is certain that y takes the value 1. Okay. So this random variable again takes value 0 and 1. Probability that y equal to 1 is 1. Probability y equal to 0 is 0. Okay. Now take z equal to x plus y. What is that? Add the two things. Right? Two matrices, you add them. So that is 3 by 2, half, half, half. It's again a random variable because it's self adjoint. So it has its values and the probabilities attached to it. So what are the values of x and y, z? You have to get the spectral decomposition of that. Okay. And I think I have not done it completely, but it is 1 plus 1 by 2 or 2 some times term V1 plus 1 minus 2. I think this is correct. So you compute the eigenvalues. I think these are the eigenvalues. 1 plus 2 and 1 minus 2. So, and you have some projections, mutually orthogonal, adding up by you get a spectral decomposition and you can compute the probabilities. So, what is the funny thing? Funny thing you see, this x takes values in 0 and 1, y also takes values in 0 or 1. So, if you have classical random variables, if you add them, x plus y would take values in 0, 1 or 2, because you have to add those things, the possible values. This 0, that 0, 0 plus 0 will give 0, 1 plus 0 will give 1, 1 plus 1 will give 2. So these will be the possible values for x plus y. Whereas for here, x plus y takes some other values with certain probabilities. Okay. So these two random variables x and y, they are not classical random variables, they are quantum random variables. So the addition gives you something else. One can get some bounds and things like that, like x plus y has to take values between 0 and 2 here. X takes values in 0, 1, y takes values in 0, 1. They can get bounds for the spectrum. But it is not true that that is in just the sum of the things.
So spectrums don't add up.
They don't add up.
Non-commutativity.
Non-commutativity. And x into y doesn't even make sense here, because x into y, if you multiply, that is not even self adjoint. Right? So it is not a random variable, it's not.